Hello everyone, my name is Songlei Wang from Harbin Institute of Technology Shenzhen. I'm delighted to present our work titled GraphGuard, Private Time-Constrained Pattern Detection over Streaming Graphs in the Cloud. Streaming graphs, where vertices and edges change over time, are prevalent in many applications such as social media, financial networks, and computer networks. Storing and querying graphs in the cloud is popular due to the cost efficiency and the scalability offered by the cloud computing. For example, Airbnb and Pixnet use the cloud as the backend to manage their large graphs. However, this approach also raises significant concerns regarding the privacy of stream graphs. According to the 2023 Entails Cloud Security Report, 39% of businesses faced a cloud environment data breach last year. Therefore, securing outsourced streaming graphs and queries is essential. Our focus is on time-constrained graph pattern detection. The task aims to continuously detect subgraphs over the string graphs that match a given query pattern. Here, the match includes three parts. Firstly, the graph structure is matched. Secondly, the labels of edges matched. Thirdly, edge occurrence orders adhere to the timing order constraints specified by the query pattern. Here is an example of a stream graph. We model each edge independently, with each edge having two endpoints to indicate the connection relationship between them. In addition, each edge has a label to indicate the type of connection between two vertices. Each edge also has a timestamp to indicate when the edge emerges. For example, E1 appears at timestamp 1 and is an edge with label 005 that connects the vertex with ID 7 to the vertex with ID 8. Time-constrained pattern detection operates on each snapshot. The query pattern consists of three components: the target structure, the target edge labels, and the timing order constraints. The timing order constraints specify the sequence in which edges must appear in the matches. This is a time-constrained match of the query pattern. Here, E1 matches sigma 1, E5 matches sigma 4, and so on. Most related works focus on privately querying static graphs, such as private subgraph matching and shortest path search. However, no prior work addresses privacy-preserving time-constrained pattern detection over streaming graphs. Therefore, we designed GraphGuard, the first framework for this problem. This is the system architecture of GraphGuard. The regulator wants to leverage the power of cloud computing to manage the streaming graph and alert when the specified patterns occur in the streaming graph. GraphGuard adopts a distributed trust architecture where the power of cloud is split into three servers. In addition, GraphGuard considers a semi-honest and non-including threat model. For the stream graph, GraphGuard protects each edge label, hides the connections between vertices, while treating timestamps as public since cloud servers can infer them from the upload time of the edges. For the query pattern, GraphGuard additionally protects the time order constraints between each pair of edges. During online detection process, GraphGuard hides the search access patterns. We use replicated secret sharing as the basic cryptographic tool. Next, I introduce the detailed design of GraphGuard. Firstly, I will introduce how to protect the streaming graph. GraphGuard processes each edge independently, facilitating dynamic updates, and uses RSS to protect the private values. However, to achieve efficient equality test in the secret sharing domain, GraphGuard encodes each private value into a one-hot vector. Then I will introduce how to protect the query pattern. I first introduced how to model the query pattern. Note that modeling the labels of the query pattern is easy as they are value information. However, modeling the structure and the timing order constraints is challenging because it requires consideration of how to handle them in the secret sharing domain. To check graph isomorphism, a common strategy is construct the search tree along the connections between vertices. However, this is difficult to achieve in the secret sharing domain. Therefore, we propose a new data structure, endpoint adjacency matrix, EAM, to model vertex connections. With EAM, checking graph isomorphism can be simplified as the comparison between their EAMs, consisting of only basic XOR and AND operations. When designing the concept of EAM, we enumerate all possible cases of connection relationships between two edges and assign a 4-bit element to each case. For example, if the sources of EI and EG are connected, the first bit of EAM MIG is equal to 1, otherwise it is equal to 0. To model the timing order constraints, inspired by the plaintest method, we first decompose the query into timing-connected subqueries. In each DC subquery, there is a straight sequential timing order relationship among all the edges. This is an example of query pattern decomposition. In this example, the query is decomposed into two subqueries, Q1 and Q2. Q1 consists of edges sigma 1, sigma 2, and sigma 4, as there is a strict sequential timing order relationship among these three edges. After modeling the query pattern as introduced above, the private values in the query pattern are secretly shared among the cloud servers. I now introduce how to securely detect time-constrained matches over each secretly shared snapshot. First, I introduce the workflow. Given a secretary snapshot and a secretary TC subquery pattern, the cloud servers securely fetch the matched edges from the snapshot for each edge in each TC subquery pattern. After that, the cloud servers construct candidate partial matches by the edges from different matched edge sets that obey the timing order constraints of TC subquery pattern. The cloud servers then securely fill out candidate partial matches whose structures are inconsistent with the corresponding TC subquery patterns, using the concept of EAM. Finally, the cloud servers securely check the timing orders and structure compatibility among secured partial matches to produce the detection result. In the first phase, we design a secure equality test protocol that allows the cloud servers to obliviously determine whether two secured labels are identical. After that, one method is to let the cloud servers directly reveal the test results, but this would leak the access pattern. To address this issue, we propose an obliviously dummy edge padding protocol to hide the access pattern. This method allows the cloud servers to safely reveal the results and identify the matched edges. In addition, we design a protocol to decide the number of dummy edges to balance the trade-off between efficiency and privacy. Our idea is to draw numbers from a discrete Laplace distribution to ensure that the leakage about the frequency of edge labels is differentially private. Please refer to section 5 of our paper for the proof of the DP guarantee. I now present the performance of GraphGuard. We use 3 graph datasets of varying sizes in the experiments and construct the baseline using the widely used MP-speed framework. This is the comparison of query latency. The results show that GraphGuard significantly outperforms the baseline, achieving a notable speed-up ranging from 29 times to 60 times in query latency. This is the comparison of server-side communication costs. We can observe that GraphGuard also significantly reduces communicating costs, with savings ranging from 96% to 98% compared to the baseline. In summary, GraphGuard is the first framework for privacy-preserving outsourcing of time-constrained pattern detection over streaming graphs. For future work, we can consider adding support for multiparty security or handling vertex or edge deletion. Thank you for your attention. Feel free to contact me if you have any questions.